Hey guys, welcome to our crash course on experimental design. So what if someone came up to you and said, eating carrots every day will cure your vision, which is what my mom told me when I was 5. Or drinking alkaline water is the way to go, those expensive $5 a liter essential bottles, or eating beef leads to increased cancer. Or maybe on a more serious note, vaccines lead to autism. Or today, social distancing leads to decreased virus transmission rates in cities. How do we know these claims are true? We can only know something is true if we can see how it was tested, the experiment, and that way we can know if the design was valid, then the results are valid and we can prove causation. Super important because we're living in a world where people don't believe science. But if people were empowered to know about experimental design, they would know what to trust. And now you will know what to trust. Knowledge is power. Just to jog your memory, back in the beginning of the year, we talked about this. We had some Simpsons fun practice. So I'll throw that in there just for you to look at, just to remind you. So today we're going to look at a few experiments and discuss key aspects. Experiments are designed to show cause and effect, causation between two different variables. We call these two variables the independent variable, the cause, and the dependent variable, the effect. So take a look at these 3 trials. Got some plants going on. What 2 things change between the variables? And those things are our variables. Take a minute. Okay. We see that the fertilizer changed, and then we also see that the plant is changing. So we got 2 things changing. Those are our variables. Everything else is staying the same. So of the 2 things changing, which one caused the other? Did the taller plant change the fertilizer? No. Okay. Obviously, it is the fertilizer changing that changes the plant height. So the fertilizer is the independent variable, the cause, the change, and the dependent variable is the height of the plant. Everything else in this experiment is held constant. Nothing is changed. That's how we know nothing is interfering how independent and dependent variables interact. Wouldn't it be shady if fertilizer A was Miracle-Gro and fertilizer B was generic, but Miracle-Gro decided to give their plants more water and more sun? How would we know that Miracle-Gro really works? And this has happened, especially when you're talking about products that are trying to prove that they are better than the others. How do we know that everything in that experiment is held constant? One thing that you can do is you publish your experimental design, then some independent, unbiased party should be able to repeat your experiment and get the results, okay? So back to it, all the other variables have to be held constant. So what are the things that are being held constant in this experiment? What's staying the same? You tell me, what could affect plant growth? We've got, light, water, the pot, the soil. You can talk about the air. You can talk about the climate. Type of plant has to be the same. That would be shady. All constants. Okay, so I'm gonna ask you to pause real quick, read the paragraph to yourself, and then we are going to go over the answers. Okay, are you back? Did you pause? Did you read? All right. So what is the cause? We see 2 things are changing between the trials. We have the plants, some plants are by a window, some plants are by a dark closet. She's trying to measure their growth. So the cause here is going to be the amount of light they are receiving. One's by window, one's in dark. And the effect is obviously the plant growth. What's staying the same? I've looked for anything that says identical. Identical pots, same soil, same species of plant. They are both coming from the same place, local nursery. And she's measuring them the same time, okay? So the dependent variable is what you are measuring and observing. That's the dependent variable. We know that she was observing the plant's growth and measured their growth. Therefore, that is the dependent variable. If you are getting this information in a table, it's going to be the independent variable is the left, the cause, temperature, and the dependent is what is result. On a graph, you have your independent variable on the x-axis, dependent variable on the y. Once you have determined, let's talk about hypothesis. So the independent, how would you put these in a cause and effect relationship? Okay, fertilizer and height of the plant. What is their relationship? If you add fertilizer, increase the fertilizer, then what will happen to the height of the plant? If fertilizer is changed, increased, then the dependent variable, plant growth, will increase, right? There's a positive relationship. A different type of hypothesis that you can write is called the null hypothesis. You are betting that the change will have no effect. So if fertilizer is added, then there will be no effect on plant growth. So 2 ways you can write your hypothesis: if, then, or if, then there will be no effect. The most important thing is that you add those change variables. Increase, decrease, the independent variable, increase, decrease on the decrease. If my calories consumed decrease, then my weight will decrease. Or is that true? That's another discussion for another day, but calorie restriction has actually shown to result in long-term weight gain because of the decrease in metabolism. Okay? All right. Hypothesis can also be viewed as the question that the experiment is trying to answer. So let's take a look at this question. We got a situation. The petri dishes in the picture were filled with the same radish seeds. Each petri dish was filled with water with different amounts of salt, 0, 0.5, 1%. The student observed the germination rate every 2 days for every 2 weeks. So here, what is the independent variable? What's the cause? It's the salt. The dependent variable, what are we seeing as the effect? What are they observing? The germination rate. Are these seeds germinating, growing? So our question is, how does blank, salt, affect the germination? So our hypothesis, if salt increases, then germination will what? Decrease. Trying to prove a negative relationship. This increase of a bad thing is going to make a good thing go down. Okay, control groups. So every experiment needs a control group, and the APES exam, they want you to have at least 3 different groups so you can have valid results. So your control group is the trial that has all constants, but none of the independent variable. So, this just makes me laugh. You know those those advertisements that show my product versus generic? Well, that's not valid. They should actually have a control group, product, generic, and then what if there was no product? You know, who knows if your detergent is better than this? Who knows that actually if you just wash with water, there would be no difference. So here, which group is the control group? The thing that doesn't have what you're testing, fertilizer. So the control group is going to be trial 1. And the constants are, of course, in every single trial. So which trial? Yeah, trial 1. It's the control group. I gave it away. Okay, take a look here. Concentration of gases in atmosphere were altered. Ooh, and the plants were observed for a month. We observed something. We just observed the plants, the results. What's the independent variable? What are you changing? The concentration of gases. What are the constants? What's the same? It looks like we're using the same plant, we're using the same air, you know, all of that. And the dependent variable, which trial contains all the constants but no change to the concentration of gases? I guess we are in trial 2. Is that what this is asking? I guess. Okay. Let's skip this for now. Obviously, when you're done, you can draw a conclusion from the results. So taking a look at the results, you can see which one was the best. fertilizer. Did we see an effect between the control group and the fertilizers? Yes, we saw fertilizers cause growth, but which one was better? Fertilizer B. So, B, okay? In order for an experiment to be valid, it's important that your samples selected are random, okay? So, for example, at Kimball High School, if we wanted to test college readiness, we, across the student population, we can't select from the 10% top to rank. We should select randomly. Or if we want to test, like, oh, are students liking education at Kimball High School, we should sample the whole population randomly, not just the top 10%. Which group would have the most representative results out of groups 1, 2, and 3? Group 1, you're only testing one plant. Group 2, you have 2 plants, but group 2, you have a lot. So group 2, because you have more plants, larger sample size, you will be most accurate. Never just have one of each, okay? So when you're designing your method, you can design your procedure. You need to design a controlled environment, have a control group, change only one variable, have multiple groups, multiple trials, and have a large sample size. And we saw that in our experiment of fertilizer. We used multiple plants. We changed only one variable, which is the fertilizer. And we had a control group, which is the one that had no fertilizer. And to increase the accuracy, we could repeat this experiment 10 times, and we should have the same result that fertilizer B would grow, whatever. Fertilizer B would cause the most growth. Therefore, fertilizer B is the most beneficial. So for your benefit, I have this cheat sheet that will go over the key points of the experimental design. And now, if you're ready, go to the I do, where we actually apply what we learned to a real FRQ. Thank you, and get ready to change the world.